Hi, this is Jiezhang, and my co-author is Suman Datta, and we are from George Mason University. So I'm going to talk about what can homologous eruptions tell about the origin of coronal mass ejections. Homologous eruptions means CMEs and flares that are very similar or are identical. They appear to be similar in X-rays, flare ribbons, and also the CMEs. Particularly, they come from the same active region. So why they are important and useful? So for understanding solar eruptions, there are two key questions we need to answer. The first question is, what kind of long-term magnetic evolution on the surface of the sun lead to the formation of the eruption structure in the corona? Secondly, what is the eruption structure in the corona just prior to the eruption? So this relates to the triggering mechanism of the CMEs. To answer these questions, we use the homologous events. So the second part of this presentation is to talk about our observational results. In the end, discussions and conclusion. So before we go to details, I want to provide two keywords for you: flux cancellation and magnetic flux slope. These are the key results of this work. For the details of what I'm presenting here, you can check out the paper just came out this year by Datta and Zhang. So the two key questions we want to address. The first question, what evolution leading to the formation of the eruption structure? There are many studies on this topic, but I think we can simply classify them into two camps. The camp one, the flux emergence model. Camp two, the flux cancellation model. So the camp one here, assuming that the eruption structure is emerged from below, either as a whole or partially. The camp two assumes that the eruption structure is formed through the surface motion, through the magnetic motion on the surface, including, for example, the shearing motion and the cancellation or converging motion. So the shearing motion plus the converging motion cause the cancellation of the magnetic flux, which ends up forming the magnetic flux slope in the corona. So these two ideas are different and contrasting with each other for question number one. For the second question is, what structure is formed right before the eruption? Also, we can simply put them into two camps. The camp one is a sheared magnetic arcade model as shown here. The structure appears to be a long sheared arcade above the polarity inversion line, and the overlying field is a potential. The second idea or second camp is the magnetic flux slope model showing here. So the property of the magnetic flux slope is a twist. So it's a twisting field among a common axis. There are many studies, observations, and the theories. So there are competing ideas for the structure right before the eruption. So which one is correct? To answer these two questions, we use the homologous eruptions. To be more specific, let's define the homologous eruptions as consecutive CMEs originating from the same location of the same active region, associated with flares of similar intensity profiles, having similar chronographic observations, and also have similar dimming and photo points in UV imaging. So this is a definition of the homologous eruption. And they are useful because they are of long term. The multiple homologous eruptions can happen within days. The days of evolution tell us what kind of surface magnetic evolution, emergence, shearing motion, or cancellation leads to the eruption. That's the question number one. Secondly, homologous eruptions are repeating. The earlier eruption presumably clears up the eruption structure in the corona, and a new reformation from a newly potential, near potential state shows with certain clarity what is the eruption structure before the new eruption happens. So in this study, we use the 3 homologous eruptions coming from the active region 11429. So this is the movie of several days of evolution of this active region. So this is a very large, very complex active region, and also is very active. There are many papers on this active region. The table on the left shows a list of the major flares coming from this active region. As you can see, in total, there are 17 M-class and X-class flares from this region. 3 of them are X-class flares. The 3 homologous eruptions we are talking about are the number 14, 15, 16 here. So there are 3 flares, CMEs, occurring on the day of the March 2012, the 7th of March, 9th of March, and the 10th of March. The first eruption happened on the 7th of March. The second eruption happened 50 hours later, and the third eruption happened 38 hours after the second eruption. So in total, the 3 eruptions occurred during a period of 4 days. So here shows the X-ray intensity profiles for the three eruptions, eruption 1, 2, and 3. So the second row shows the flare ribbons in the blue color coming from the AIA 1600 angstrom images overlaid on the HMI magnetogram. Here shows the coronal dimming coming from these 3 events. As you can see, the X-ray profiles are similar. The location of flare ribbons are similar. The morphology also similar. The post-flare location are very much similar within 4 days, and the dimming and also the coronal waves are also in the same direction. So they are definitely homologous events. Similarly, for the CME observations, for the event 1, 2, 3, this is the white light pornographic observations of the eruptions. As you can see, they are all fast CMEs. Speed is more than 1800, 950, 1200 kilometers per second. And seen by 3 chronographs, stereo B, SOHO, and stereo A. As you can see, they are all halo CMEs, have very similar morphology. So these are the 3 homologous events we are talking about. So this slide shows the one example of the eruption from the disk observations. The event number 2 happened on March 9th of 2012. So in these composite images from the AIA 94 angstrom of the 6 million degree AIA 131 angstrom from 10 million degree, AIA 171 from 1 million degree, and AIA 1600 for the transition region images, magnetograms, and also the X-rays and the ribbons. As you can see, these observations in a cadence of 12 seconds provide a lot of details of the structure before the eruption, days, hours before the eruption, right before the eruption, and also during eruption. For example, you can see that during eruption, there are the diffused features coming out from the platinum inversion line region. These are the actual eruption structure we'll be seeing in white light. So these detailed observations give us a lot of information about the 3 eruptions and their evolution. So now let's look at the evolution of the magnetic flux. Again, on the right side is the movie of the HMI every 45 minutes over several days. Again, this is the complex active region. But let's look at the overall flux of this active region over many days. As you can see, initially there's a flux increase. The black line is the total flux. The red line is a negative flux. The blue line is a positive flux. For the first few days, we can see a continuous increasing of flux, this flux emergence. then reach the peak, then decreases. The first eruption, event 1, occurred during the emergence phase of this active region. However, for the second event and the third event, there's no more flux emergence. The flux starts to decrease continuously. So let's look at more details how the magnetic flux evolved during that several days. The movie here shows the velocity field of the active region from the correlation tracking methodology to derive the velocity field on the surface based on the features on the disk. So it's pretty complicated, but you can see all kinds of evolution, including the rotation motion, shearing motion, and if you look carefully, you can see the converging motion. So it takes a lot of time to inspect this kind of movie. However, let's put things simple. So we simply measure the distance between the polarities, the positive polarity and the negative polarity. Those are the two main polarities that produce the eruption. Here is the polarity inversion line, that where the eruption originates. The distance is measured over here. As you can see, the distance between the two main polarities, opposing polarities, are decreasing after the first event. So they're decreasing. Similarly, the total flux also decreases. So this is the strong evidence that the converging motion, is specifically the flux cancellation happens over here, leads to the eruption formation of the eruption structure. The flux emergence is not the key. Flux emergence does occur and is important. However, the flux emergence does not guarantee the eruption. On the other hand, in order to have the eruptions, you have to have this kind of the flux converging motion and the flux cancellation based on these the three homologous events. So now let's take a look of the coronal structures prior to the eruption. So here are the images for the event 1, 2, 3, the AIA 131 10 million degree image. The middle column shows the temperature map of these three events right before the eruption. Again, it's very hot, it's more than 10 million degree. Now the core feature right above the polarity inversion line is become more obvious. This is X-ray images from the Hinode XRT and also the GHOST SXI. Clearly, there is existence of EUV hot channel showing here about 10 million degree temperature for each of the three events. There's also evidence of the existence of X-ray sigmoid for each of the events before the eruption. Thus, we can conclude that the hot sigmoidal structure along the polarity inversion line exists right before the eruption, which is a strong indication of the magnetic flux ropes. By the way, after each of the eruptions, these structures disappear quickly, and then they reform over the 20 hours and 30 hours to reform this kind of the sigmoidal structure. So we believe that this long-term evolution of the flux cancellation eventually leads to the formation of a sigmoidal structure, which is a magnetic flux rope. To provide more evidence to that, we use the on the left side we show the vector field. So the arrows here shows the horizontal magnetic field overlaid on the line of sight magnetic field from the HMI observations. Using the vector field as the boundary condition, then we can apply the nonlinear force-free extrapolation to get the coronal field. As you can see that in large scale, the coronal field is nearly potential. However, along the polarity inversion line, in the core region, you can see the field line is highly shielded and also kind of twisted. So this is another evidence that twisted coronal field above the polarity inversion line, as extrapolated from a nonlinear force-free model, indicates the likely presence of a magnetic flux rope right before the eruption. So here is the scenario based on all these observations, the HMI, the AIA, and the chronograph observations, and over many days, to put all this information together, we provided this scenario for the homologous events. First, after each eruption, the coronal field returns to a near potential state. Then, continued converging and shearing motions produce highly sheared coronal field. Eventually, this continuing cancellation and shearing motion produce a larger scale coherent magnetic flux slope in the corona. Then the instability of the magnetic flux slope, possibly, for example, through the torus instability, triggers the eruption. The eruption of the flux slope leads to magnetic reconnection, which rapidly adds colloidal flux onto the magnetic flux slope and strengthens the instability. So this kind of the rising motion of the magnetic flux slope and the magnetic reconnection is a positive feedback process. In the end, this positive feedback process produces the CME, the flare, and other phenomena associated with eruption, including coronal dimmings, coronal waves, and other phenomena. When this is done, return to step one, that's back to the potential state. Then the converging motion, shearing motion continues and form another eruption after 10 hours or 20 hours, depending how fast the converging motion persists. So with this scenario and with these observations, we have two conclusions, which are related to the two questions we raised earlier. To the first question, we find that persistent flux cancellation and the shearing motion is directly responsible for the reoccurrence of major eruptions. This result indicates that the flux cancellation is the key process for the formation of the erupting magnetic structure. The key process is flux cancellation, it's not the emergence. Answer to question number 2. Right before each eruption, a new magnetic flux loop is formed, as manifested by long hot channels in EUV, sigmoidal structure in X-ray, and a twisted magnetic field above the polarity inversion line. So this indicates the importance of the presence of magnetic flux loop for triggering the eruption. So this is our two major results coming from a study of 3 homologous events. Again, for more details, please refer to this paper by Dr. and Zhang in 2020. Thank you very much.